So this is the SLO problem, the student learning outcome problem number 2. It's optimization, where you have this setup. A rancher has 200 feet of fencing to enclose 2 adjacent rectangular corrals. What dimensions should be used so that the enclosed area will be maximized? This is from section 2.5 in your book. There's not an exact problem, but the same ideas are going to be worked on here. So here is our problem, and when I take a look at how to set this up, first thing I want to do is I want to draw the situation. So here we have rectangular corrals. Okay, so just imagine some sheep or some cows and some horses, something like that. I guess sheep aren't very popular right around here. So if I let this leg be X and I let this longer side to be Y, we know that we have 200 feet of fencing, and that's it. We just have 200 feet of fencing that will go all the way around and do this one X size in the middle. So I've got 3 X's and I have 2 Y's. And the total perimeter is 200 feet. So that is actually what's called in section 2.5 a secondary equation, the secondary. Now, you're always going to have more information for that. Sorry, I marked out secondary. I meant to do underneath. But so for our secondary equation, you're going to always have more information. The one that we're going to find the derivative of is area, because the wording here says that we want the enclosed area to be maximized. So this is just going to be X times Y. And we could also think of it as 2xy. That would be, it is just going to be X times Y. I was thinking of a different way that I work out this problem sometimes, but in this case, yeah, it's just going to be X times Y. So for here, this is the primary equation. So our primary equation, our secondary. So what we need to do with the secondary equation is I need to solve for either X or Y. In our case, I'm going to solve for Y. So I'm going to bring 3x over to the right-hand side. I'll have 2y is negative 3x plus 200. Y is negative 3 halves x plus the 200 over 2. Remember, when you divide by 2, you're going to put it under both parts. So this equation is this. That's what y is equal to. Now, I'm going to take my secondary equation and I want to put it into, substitute into my primary equation. Really straightforward in so many ways, because what happens then is I have x times negative 3 halves x plus 100, which is negative 3 halves x squared, really bad 3 there, plus 100x. So turns out this is the area equation. We now have it just in terms of one variable, which is how this section works out. You start out with two variables that you want to be maximized, but we need to rewrite things to get it all in one terms of one variable. At this point, I'm going to now find my a prime. I want to find the first derivative. That's going to tell us how to maximize. So we end up having, bring the 2 out front, take away 1, so that's going to be negative 3x plus 100. We are going to set this equal to 0 and solve for x. And what we'll have is that x is 100 over 3. Now, we also know in this section that we need to, anytime we're maximizing or minimizing, we need to be able to take this and either use the first derivative test or the second derivative test. In my case here, I'm just going to use the first derivative test because there's a little more work that I can do, and I find that students usually get it a little better, but the second derivative test is actually a lot faster. Here is I'm going to do the first derivative test. Now remember, with the first derivative test, that means that we are demonstrating that this is indeed a maximum. All right, so this is approximately 33 1/3. So I was about to write 0.3, but yeah, it's 33 1/3. So I can make this test point to be 30 and this one to be 40. I plug this in, so I see a prime of 30, and a prime is over here, so that's going to be 10. A prime of 40 is here, and I'm going to have negative 3 times 40 is negative 20. So since this is less than 0, this is greater than 0, what's happening is where 30 is, it's going up because this is plus, and over here it's going down, so we have a minus. Now remember, the first derivative test says that if you increase then decrease at a particular critical point, then you do have a maximum. So what this means, this says that we have a max at x is equal to 100/3. All right, so once we do that, we then need to just take this information and we're going to use the y that we found, which was y is negative 3 halves x plus 100. So that's negative 3 over 2 times 100/3 plus 100. The 3 cancels. The 2 goes into 100, gives you 50. We have negative 50 plus 100, which gives us 50. So our x is 100/3, our y is 50, and if you wanted to know what the area is, what the max area is, even though in this case you're really just wanting to know the dimensions, but some of my MATLAB problems ask for the actual area. Area is going to be 100/3 times 50, and this is approximately 1,667 feet squared. Thanks.